Next up, we have our next lightning speaker of the day, Nadya Chernyavskaya, Manager of Predictive Product Development and Innovation at Total Energies Gas and Power. She leads the development of production-grade AI software for forecasting, seamlessly integrating cutting-edge machine learning with business intelligence. Her talk is titled, Making Renewables Profitable with Automated ML Forecasting. Take it away, Nadya.
Thank you very much for this nice introduction, and it's really a pleasure to be here and give you an industry perspective on the renewables and automated ML. So I'm going to start by saying probably something rather obvious. Electricity is everywhere in our lives, from the moment we wake up and turn on our lights, to cooking our breakfast, and of course, charging our ubiquitous screens. Industries rely on it to manufacture goods, and hospitals rely on it to save our lives. And since 1980s, electricity demand has tripled, and it's expected to double again by 2050 as more sectors electrify and, of course, digitize. So this wonderful electricity that we rely on so much has to come from some form of energy. And historically, it's been coming from fossil fuels. If you look at the world mix in 2010, we see that more than 60% is coming from coal and natural gas, and renewables contribute to only a fifth. Fast forward to 2024, and thanks to a global decarbonization efforts, we see that coal has dropped to 34%, and the renewables now contribute to a third. In the last decade, the world has been investing in renewables. And this plot tells us a compelling story. The capacity shown in orange has skyrocketed since 2010, and the solar costs in blue have dropped 90%. Solar is the fastest growing energy technology in history, and the wind is not far behind. And while this all sounds like really great news, there is a challenge. And this challenge is intermittency. The sun doesn't always shine, and the wind doesn't always blow. But our electrical grid must stay perfectly balanced, because unlike water or gas, electricity cannot be stored at scale, at least not cheaply and efficiently yet. And every second, the amount of electricity generated has to equal to the amount that is consumed. And if it's not, and the demand, for example, suddenly spikes due to a heat wave, and the supply cannot keep up, then this price will surge and blackouts can happen. And sadly, this intermittency leads to a profitability challenge. Why? Because renewable power plants are huge investments. And due to the intermittency that we talked about and the recent extreme weather volatility, the energy prices have been fluctuating wildly. In some markets, the price can spike factor of 10 or even 100 over the course of just a few hours because the wind's still blowing. And because of this, the revenue from the renewable energies are unpredictable. And because of this, renewables are still seen as financially risky. And many companies, many energy companies are hesitant to invest or stopped investing altogether. So it is a huge problem. So the question is, what can help us make the business of renewable energy more attractive to investors such we can actually accelerate the energy transition that we need so much? Well, given the title of this talk, I think you guessed it, it's forecasting. Forecasting is a powerful tool that can help us make the business of renewable energies economically viable. First, we can forecast electricity consumption. This can help us plan ahead and avoid costly overproduction and last-minute purchases. Another use case is predicting prices or market trends. And that's important not just for short-term trading. It's also critical for hedging long-term contracts. Often, large renewable energy producers, such as wind farm owners, will sign long-term contracts with large energy buyers, like data centers, contracts for 10, 20 years. And if you're locked in a long-term deal like this and the energy prices keep fluctuating, it might become unprofitable very quickly. So hedging is very important. Finally, if we can actually forecast when the grid will be undersupplied or oversupplied, we can charge our batteries optimally such that we can help balance the grid to ensure that the price doesn't explode and the blackouts don't happen. Batteries is the new way of storing electricity, and we must do so intelligently. So with these examples, I hope to show you that accurate forecasting can help us reduce the risk, and therefore it can lead to a more stable revenue associated to renewable energies, and therefore it will bring us closer to a fully decarbonized grid. All right, so forecasting it is, but which approach should we take? There are two main approaches, physics-based and data-driven. And the former one is based on physical laws and system parameters. It can work very well in simpler, well-defined systems, but sadly, it often struggles in complex and real-world conditions. On the data-driven side, we have statistical models such as ARIMA. They work well, again, on simpler seasonal trends, but they will struggle with nonlinear and high-dimensional patterns. ML, of course, as you know, can capture complex and nonlinear relationship and learn from data. And learning from data and adapting to new patterns is exactly what we need in these highly volatile times. All right, for ML forecasting, but which model? That's the next question. Of course, you can go straight to the coolest kid on the block and go for transformers. But is it really what you need? Often, the only thing you actually need is the decision tree-based models. Decision trees excel with medium-sized tabular data and often are the real workhorse behind the performing models in the industry setting. But hold on a moment, you will tell me, decision trees don't naturally handle this time dimension of our time series data that we have. And here, this trick is to intelligently integrate this time-related information as features. We can add things like lagged values, so the values from 1 month ago, 2 months ago. We can do all kinds of rolling averages and trends. We can add categorical variables such as hour of the day, months of the year, etc. By doing this, we transform our time series data into tabular data for which the tree-based model works so well. So now I would like to show you 3 real-world examples for which forecasting with decision trees works so well. So power consumption forecasting is your classical time series example. But once you integrate this time-related information as features, what you actually do is you transform this time series forecasting problem into a simple regression problem. You simply predict a continuous variable, simple regression problem. Market trend forecasting is another one. Let's look at this. Traders often come and they ask, what will the energy price be? But forecasting the energy price is hard. And the question is that really what they actually need to know? And the answer is no. Most of the time, what they really want to know is on which of the 2 markets the energy will be low, such that they can buy it on the market where it's lower. So when you reframe the problem like this, it actually becomes a classification problem. Forget forecasting or predicting direct continuous values. You just want to classify, is it market A or market B on which the prices will be lower? Finally, anomaly detection. Can forecasting even help us with anomaly detection? Forecasting with trees can help us with anomaly detection. Renewable power plants are actually complex systems, and they need frequent maintenance. And unreported and therefore unexpected failures and maintenance will lead to downtime and unexpected losses of revenues that we need to investigate. We have dozens of different renewable power systems on our portfolios, so we need to timely identify these type of anomalies in the power output and then act accordingly. So it's a clearly an anomaly detection problem. But we can actually solve it with the quantile regression. What we can do is we can use quantile regression to predict the lower bound of the power output. Once the actual generation falls below this low bound, we will flag this as an anomaly. As simple as this. So 3 examples how forecasting with decision trees can be solved as a regression, classification, anomaly detection. All right. So now, let's say ML forecasting works very well for us. But here is the catch. Building a good ML model takes time and expertise. What if you have hundreds of different use cases? And we, as a global integrated energy company, we operate across dozens of markets across the whole world. We have a large portfolio of renewables, such as solar, wind. We also have our batteries. So each region and the market, and even renewable asset type, will have different patterns. So each of them will need a separate model. So if we want to scale to all of these hundreds of use cases, we would need an army of data scientists, which, believe it or not, we don't have. So how can we move beyond the isolated proof of concepts and make forecasting our core capability? Well, we need automation of some kind. And that's where AutoML comes in. AutoML can do all the heavy lifting. It can automate feature engineering, model tuning, and selection. But it doesn't just speed things up. It enables consistent modeling and rapid iteration with fewer mistakes. AutoML is a framework that can help us to move from the isolated proof of concepts to actually deliver directly production-grade models. So now, in this last few minutes of the talk, I want to highlight what was important for us when we built this system and how we operated. So the very first question that we should ask ourselves when we build a new ML software product is, well, who we are building it for. And time series forecasting is actually quite a bit harder than other ML problems, often because it has many pitfalls. Leaking future data is one of the very common pitfalls. Over backtesting is another one. So when you build an AutoML framework, that obviously will incorporate all of the main components of your typical data science LML pipeline. You should keep 2 types of users, 2 types of data scientists that all of us have in our teams in mind: the junior ones and the senior ones. The junior ones will need safeguards against common errors. They will need automated validation logic, reasonable defaults for hyperparameters and search spaces if you do Bayesian optimization, etc. Senior data scientists, on the other hand, will want to have full control. They will want to be able to experiment with their new ideas. They want to have this flexibility. So AutoML shouldn't just automate. It should standardize the best practices while at the same time providing this flexibility to experiment with novel ideas. So what was proven to be very important for us is the following list. I'm going to go one by one. First is having pipelines that are fully configurable. Being able to spin up trainable runs where simple editable JSON configs means not just fast onboarding of new users and new use cases, but also no duplicate code and no reinventing and rewriting the same logic every time for every use case. But of course, configs are not enough. You also need modular components. Basically, every important step in these pipelines that we've seen should be a pluggable Python module. If a data scientist wants to override a default loss functions, they can. If they want to add a sophisticated feature, they can. They should be able to extend easily. Of course, we containerize the whole system to have consistent behavior no matter where you run it. So you no longer will have, well, it worked on my machine types of issues. Built-in visualization is another key area. When you have dozens of models being developed or running, you need a tool that is already there for you to quickly inspect the performance and diagnose issues. You don't want to go and dig through 15 different notebooks. data being the foundation of any ML model, you want to have a common and extendable data lake that is shared across all of these possible use cases that you have. Of course, you will also need to top it up with the robust missing data handling. Finally, and what really makes the difference here when you have a system like AutoML is that you don't need to have a separate handoff from your data scientist notebook to a software engineering team. Once the model is trained, it's ready to be deployed. So the data scientist that has the domain knowledge owns the model end to end. Cherry on the cake, you can build a system like this using common open source components and then deploy it on your favorite cloud provider. So what's proven to be important for us is not just clean code or smart models, but a robust modular system that keeps performing even when scaled to hundreds of use cases. And that already brings me to my summary. And the 3 key messages that I want you to retain here is that while, yes, accelerating energy transition is a must, there are still challenges related to profitability of renewables. And forecasting can offer us a way to make renewables profitable and help accelerate the energy transitions. ML doesn't necessarily mean deep learning. You can use decision trees and reframe problems very efficiently. Finally, scaling ML in industry is really critical. In our case, AutoML enables us to have efficient and scalable solutions. So thank you.
Thank you very much, Nadya. That was an excellent presentation on a very important topic. You touched on so many things that I think a lot of us have encountered in our careers, which is going from POCs to production is not necessarily easy. So with that, I'll open it up to questions from the audience. And I'll start with something from the Hoover app. Could your anomaly detection approach have picked up the blackouts in Spain and Portugal?
So in this case, what we use anomaly detection for is rather to do post-analysis, so post-anomaly analysis, because you saw, right, we compare, so we predict, right, and then we compare to what actually happened, and then we can then analyze it, given that we have hundreds of different renewable power plants, we need to keep track of everything that happens. So in this case, it's not a proactive anomaly detection, right? Because I think the question is rather about proactive anomaly detection. Like if you're looking at the data streams, can you actually identify the anomaly is about to happen? So you have anomaly in other data streams that are kind of preceding the actual anomaly. So this is not what we were doing in this case. So it was really like, if you have hundreds of different power plants, different sites across all over the world, how can you identify that they are working as expected because they have different owners, et cetera? So you have like this automated system to make sure that everything is working well.
Great. Is there a question from the audience? There's one in front here. Oh, I think there's one in the back.
I have one general question related to the topic, not specifically to AutoML, which you explained very nice. It is about the support and renewable and grid efficiency. If we consider that we develop additional algorithm and machine learning techniques to make the grid more efficient, which is absolutely clear. But then, in order to feed these algorithms and to run machine learning on such scale, if we consider how many sources we have to invest a lot in ICT infrastructure or data center server infrastructure and to feed this infrastructure. So to use a huge amount of power in order to feed something that should, in return, make something more efficient. How we balance that? Did you run some kind of techno-economic study to see what are the gains, what we get and what we lose
It's
because,
an
for
excellent-
example, data center efficiency and green internet is my topic, so I am aware of the amount of energy that you need to put in such project. How much can we actually spare?
It's an excellent question. Thank you very much for this.
Welcome.
So what I showed you here is basically AutoML to use with the decision trees, right? Decision trees are not huge transformer models that for which even the inference will take time. It's very simple models that can be run on CPUs. So that's one aspect, that you actually use way less power when you run simpler models like this than if you want to go and talk to your ChatGPT sometimes. So that's one aspect. But the second aspect is that the reason why we wanted to have this AutoML is because we want to avoid data scientists coming in and sending all kinds of different testing runs with the parameters that don't make any sense whatsoever, right? So that's why we want to have AutoML that encodes certain good choices and has this logic that prevents you from wasting insane amount of computational resources doing God knows what, which everyone that starts in data science makes sometimes mistakes. It's normal, we all make mistakes. But here at least we say, okay, let's not make the costly mistakes that will make us waste a lot of power. So that's why we are really conscious about this. So that's why our approach is test less, but more intelligently.
Thank you very much, Nadya. Unfortunately, we don't have time for any more questions, but please ask your question later. I'm sure Nadya will be